our previous two discussions, we made a very good study of electromagnetic radiation in the context of waves, a concept that we already understood from our discussions of sound. We also realized that there's a description of electromagnetic radiation in the context of photons. In either case, we've discussed and defined the frequency and the wavelength and their relation to the speed of the waves. We understand that these waves carry energy through space without the need of a medium. And so what remains for the rest of our study is to investigate all of the phenomenon that we observe with respect to the behavior of light. For human beings, visible light is a particular issue because the rods and cones of our eyes are sensitive to a very narrow band of wavelengths, and this is one of the chief ways that we receive information about our world, and that is the visual sensation. And so we look around our universe, and as is the purpose of physics, we seek to describe the everyday things that we observe in the nature of light. For example, I can see a wall, and I can see the mirror that hangs on the wall. The explanation for the sensation of vision must come from light enters my eye from the object that I'm observing. So there's light that comes to my eye from the wall. There are lights in the room. The light travels to the wall, reflects, which is the term we use to describe the bouncing of light off of a surface. The light reflects from the wall and comes to my eye, and I see the wall. It's strange, however, when I look in a mirror, the explanation for what I see is still that light impinged on the mirror, reflected, and came through my pupil to stimulate my sensation of vision. But the remarkable thing is that an image is formed. More than just color or brightness, information is communicated in terms of familiar shapes that I observe in everyday life. So the question is, what is the difference between these two things? How is it that the mirror forms an image that I can observe? And also, what are the properties of that image? Are there any mathematical relationships I can make from that image? And why does the wall not create an image? Some objects in the universe emit light. For example, our sun emits the sunlight that we enjoy walking around outdoors in the springtime, but it's also true that a hot filament in a light bulb creates incandescent light, and that an LED, through a remarkable microscopic process, produces light. But the vast majority of things that we observe in our universe, the light that comes to us is reflected light. Reflection is how we see our world. I added the moon here on the slide, one, just to make a rather bland-looking slide prettier, but also to make the astronomical observation that while we look up at the sun and the sky and we see the sun in terms of the light that it emits, the moon does not emit visible light. Instead, the light of the moon is the light from the sun reflected off the moon. So reflection is a property of light interacting with matter, which we seek to investigate today. There is a law regarding how electromagnetic waves, and as it happens, also photons, interact with a material surface. And I'm happy to say, and you're probably happy to hear, that it is probably the simplest law in all of physics, the most straightforward and transparent equation, no pun intended, in all of our physics, and that is the law of reflection. Here, I have represented an electromagnetic wave coming in from the left. If you like, you could think of it as the path traveled by an electromagnetic photon. In many cases, both of those pictures work equally well. In some cases, one is preferred over the other. Let's think of it as electromagnetic waves. So I have an electromagnetic wave coming in from the upper left, let's say. Now, to draw that into my diagram would greatly complicate things. So what we do instead is we draw a line in the direction of travel of the wave that we call a ray. We don't draw the entire electromagnetic field. In fact, this room is full of light. And so to draw it all would basically fill the room. So instead we indicate it In the same way that when I draw an electric field created by a charge, I don't draw all of the electric field. That's impossible because the electric field is everywhere simultaneously. Instead, I draw electric field lines. The ray of light is the same principle. I've drawn a line that represents the electromagnetic radiation that's passing from the upper left, and here it comes to the mirror and it strikes the mirror. There is a line that I draw here, a dashed line, that is perpendicular to the mirror. It is called the normal line. When we were studying Newton's laws and investigating the way forces change motion, one of the forces on our list to be on the lookout for was the force of contact that we call the normal force. I impressed upon you then that the reason why we called it the normal force was that that force was perpendicular to the surface of contact. Well, the term normal is being used in the same context here. The normal line is perpendicular to the mirror. In order to describe the way in which the incident ray hits the mirror, we use the angle of incidence, which is measured from the incident ray to the normal. There's no reason why you could not formulate all the laws in the context of the angle from the ray to the mirror. But we have chosen by convention not to do that. The angle of incidence is always measured from the ray to the normal. So then the incident ray, which is made of electromagnetic radiation in the form of waves, interacts with the material substance of the mirror in a way that is complicated. The mirror is composed of atoms. The atoms are composed of charged particles. The charged particles feel forces under the influence of electric and magnetic fields, and so it is indeed quite complicated. We need not concern ourselves with that complication, however, because the observed effect, that is to say, I guess, the general effect that we see in the laboratory, is that when the ray is reflected away from the mirror, the reflected ray has an angle relative to the normal, which is aptly called the angle of reflection. And what we discover through experimentation is that the incident angle, the angle of incidence, is equal to the angle of reflection, and so I write that as a mathematical equation. You see what I mean? It's the simplest mathematical equation that you have ever seen. The angle of incidence, which I'm content to call theta I, theta incidence, is equal to the angle of reflection, theta r. By the way, I should say, while I love this diagram and its clarity, it does say that the incident ray and the reflected ray are interacting with a mirror. The law of reflection applies not only to mirrors that create a reflection that forms an image, which I'm very interested in investigating, but it's also true of the reflection of light off of any surface. So the wall that was previously mentioned, or here the board next to our slide presentation, I can see it because of the light that's reflected on it. This board and everything that I see is subject to the law of reflection, not just mirrors. But we'll see that there's a little bit of a complication. The reason why a mirror forms an image is that the mirror surface is so smooth that the roughness of the mirror is nearly equal to or smaller than the wavelength of the light that shines onto the mirror. This is sometimes called the surface roughness of a thing. So here I have a mirror, just like your bathroom mirror, hanging on the wall, and I hold up an object in front of it, and everyone knows that if I were to look into the mirror, I would see the image of the object. But what I'm interested in just now is to imagine the rays of light that leave the object and interact with the mirror. Remember, the light is everywhere. I can't draw it all. So instead, I draw a number of rays that represent the light. So as an example ray, I have the one here at the top that leaves the flame and happens to travel to the mirror. It is one of an infinite number of rays. When it travels to the mirror, it reflects in such a way that it obeys the law of reflection. The angle of incidence is equal to the angle of reflection, and it bounces back this way. That ray of light, of course, doesn't go through the mirror into the wall. It reflects. Similarly, there's a ray that goes straight at the mirror. This one is a bit curious because the ray goes directly to the mirror and obeys the law of reflection. Well, if it goes directly at the mirror, then it's hitting perpendicular to the mirror. The angle of incidence is 0 degrees, because the angle between the ray and the normal is 0 degrees. It then reflects, obeying the law of reflection, such that the reflected ray also has an angle of 0 degrees, and so that ray reflects right back again. I have two more examples at the bottom here where a ray goes down, strikes the mirror, and bounces away, obeying the law of reflection, and one at a larger angle of incidence, which then reflects at a larger angle of incidence. The curious thing here is that because of the smoothness of the mirror, when the rays reflect off the mirror, they do not become disorganized. They reflect in a very regular and predictable way. We'll come to realize that the reason why the image exists in our perception is that if I trace every single ray that I draw into the mirror as if it had come from that location in space, then I discover that those rays will reorganize themselves on the other side of the mirror, inside the wall, in such a way that the information about the object is present in the form of an image. Light does not come from this image. In the future, we'll come to refer to that kind of an image as virtual. But for now, appreciate the fact that the image is created because of the lovely, regular reflection of rays from the mirror. Surfaces like this, where the roughness is so smooth that it's comparable to the wavelength, are often referred to as optically smooth in the business of physics. But optically smooth surfaces are only one of a type. The other type is a rough surface. Well, here I have an example of well-organized light, which I've drawn here coming in from the upper left in the form of a bunch of parallel rays, and they're going to strike this rough surface here. Now, if I were to go along, and I haven't done because it would vastly complicate this diagram, but draw the normal, remember that the normal is always perpendicular to the surface. Well, when the surface is rough, every spot has a normal that is crazy. They point every which way. So this, let's take the ray that is the lowest of the rays coming from the upper left. That ray strikes the surface at an area where the normal is very much bent to the left. It obeys the law of reflection, but that ray wildly goes off in a direction far to the left. The very next ray up from the bottom strikes, and where it strikes, there is a normal to that point on the surface, and it obeys the law of reflection at that point. Well, that has it going off to the right. So two rays that had a very simple relationship relative to each other have now been complicated by their interaction with the surface. The surface has scrambled the organization of the light. And we see that happens with all of the parallel light rays. This kind of reflection that does not preserve the image is called diffuse reflection. It's the kind of reflection that I see when I look at a wall. Do not see an image of myself in the wall because the light that comes from me to the wall is scattered by the wall. It is reflected, and so it can be seen by others who are standing around the room looking at the same wall, but my image does not appear because the surface lacks smoothness. The mirror that I see when I go into my bathroom at home is a flat mirror. A flat mirror is referred to a plane mirror. Turns out it's not the only kind of mirror, and we'll save our study of more complicated situations for later. But just for now, I would like to understand about this image that appears on the other side of the plane mirror. Once again, I have a candle that I'm going to refer to as the object. The object in this case is a particular distance to the mirror. I'm going to call that the object distance. Slowly here, I'm adding in specific language and definitions because we are on our way to equations after all. But for the moment, the object is a particular object distance from the mirror. A ray going from the object to the mirror reflects back again. I'm going to provide two more rays. A ray that starts from the object and goes to the mirror, reflecting according to the law of reflection and arriving here to be viewed by the observer at point C. There's another ray, it's just another ray that I've chosen from the infinite rays available, and that ray travels to the mirror, reflects, and comes to position D here. Now, the observer is looking at these rays coming off the mirror, and it's a particular feature or fact about human vision, is that we form images only from diverging rays. What I mean by divergent is you see these rays, after they leave the object, they're getting further and further and further apart as they go. That's called divergence of those rays. And the human eye sees that divergent light. And in order to comprehend it, it traces that light backwards to the source. But without appreciating that reflection has happened, tracing the two rays, C and D, back to their source leads them behind the mirror to an image of the object, imagining, as you see, that the light has come from a location where it does not actually come from. Because of the geometry of it, and I'll spare us all the trigonometry, you can see that the ray from the object to position A and then from A to the image forms a triangle with an equal hypotenuse, such that the object distance, that is, again, the distance of the object from the mirror, is equal to the image distance. That is the distance from the mirror to the image as it appears. So as you stand in front of your bathroom mirror, the distance from you to the mirror is the same distance as your doppelganger in the mirror appears to be behind the mirror. Those distances are equal. I always find this amusing, and some people were taken by surprise when I pointed out. But if you're standing in front of your bathroom mirror, I challenge you to have a look at this. If you're standing in your bathroom mirror, simply raise your right hand. When you do, look at the person reflected in the mirror. Consider that image that you see, and you will realize that the person in the mirror has raised their left hand. You have raised your right hand, and the person in the mirror has raised their left hand. Not only that, but if you're wearing a t-shirt with some text on it, you would look at the person in the mirror, and the text on the person's shirt in the mirror appears to be reversed left to right as well. This leads people to the assumption that the mirror is doing a left-right reversal of the image. That turns out not to be the case, and I love this diagram here. It's clearly an old one. It has a very retro feel to it. Maybe it was made in the 60s or early 70s. But it does a beautiful job of demonstrating what's really happening according to that effect. When you stand in front of the mirror, your reflection is reversed back to front or front to back, however you want to look at it. I can clearly see here, instead of holding the sign up in front of the mirror, parallel to the surface of the mirror, it's been arranged here perpendicular to the mirror. And you can clearly see by some ray tracing, and I think it's very sensible. I think nobody looks at this and is confused by this. This is what you would expect to happen naturally, that the image is actually reversed front to back. The final N in inversion is close to the mirror, and the I in inversion is furthest from the mirror in both cases. And so it's been flipped front and back, not left and right.